Okay, so yes, I will. Okay, so some of you have taken logic, some of you have not. There's at least one. So let's start with a gentle introduction to logic. Today I'll be talking about propositional logic. You all can see the screen and hear me well, correct?
Yes, sir.
Yes, sir.
Okay, so first, the propositional logic, which is also, even if you have heard propositional logic, Boolean algebra, Boolean logic, two-valued Boolean logic. Okay, they're all the same or similar. So just a motivating example. So this propositional logic is used to model kind of scenarios of the kind that I'm going to be describing now. Consider this scenario. Say you have, if you train, some declarative statements, okay, that you make. If train arrives late and there are no taxis at the station, then someone, Ram, is late for a meeting. So Ram is not late for meeting, and you also know for a fact that if train arrives late and there are no taxis in the station, then Ram would be late for the meeting. So you know that Ram is indeed late for the meeting and the train arrives late, and therefore you conclude that taxis did exist at the station. Why? Because since Ram is late for the meeting, so if taxis did not, suppose taxis did not exist at the station, and since train arrives late, if taxis did not exist at the station, and together with the fact that train arrives late, the first proposition assertion makes Ram to be late for the meeting. So, and Ram cannot be late for the meeting, be late for the meeting and not. That contradicts with the other statement that Ram is not late for the meeting. Therefore, indeed, you can conclude that taxis must have existed at the station. So here's another scenario similar to one. Okay. So the scenario is similar, but the facts, the statements are somewhat different. If it's raining and when Alia has no umbrella, then Alia would be wet. And if Alia is not wet, and you know that, and the fact that Alia is not wet and it is raining. So using similar reasoning, you can conclude Alia must have an umbrella. For if it were not, then she would be wet. If indeed she did not have an umbrella, since it's raining, she would be wet. But you know for a fact that she is not wet. So the underlying structure. So these are all certain propositions that are constructed based on various declarative sentences. So the underlying logical basis for reaching these conclusions in these cases, in both the scenarios, are the same. So, for example, if you were to use A to denote the fact that train arrives late, and B that there are no taxis at the station, and C to denote that Ram is late for the meeting, okay, then this can be expressed as, the first one can be expressed as A and B implying C. And the second assertion is a conjunction, okay? It states that Ram is not late, that is the negation of C and A. And, so the question is if you can conclude from that B, which denotes there are no taxis at the station, is indeed not true. That is, taxis did exist at the station. So then, yeah, so you could see A and B, A, B, C denote different declarative statements. But in the two situations, but the structure is the same. And the reason that you can conclude in both cases not B is because, is actually, it can be expressed in logic in this fashion, okay? That it is true that based on certain propositional logic rules that if you have A and B implies C, and along with that not C and A, that you can actually deduce using the rules of logic that not B is true. In this case, the same thing can also be expressed, since in some logic, especially in classical logic, which is the one that we will be concentrating on in this course, it can also be expressed as that this thing can be stated that A and B implies C and not C and A, that it indeed implies not B is a tautology. Okay, so propositional logic can then be used for modeling these kinds of scenarios. That's the motivation for and analyzing such scenarios. Okay, and so this kind of reasoning can be then formalized and even made more formal, the modeling as well as the analysis, and the derivation of the conclusion can also be automated. Okay, so that's the purpose of using logic for these kinds of problems. So what does logic in general and propositional logic also, which is an instance, have the components? So a logic has a language of declarative sentences. What I mean by declarative sentences, things like train arrives late, no taxis at station, statements, sentences that are either true or false, okay, are called declarative sentences. And usually these things are composed from atomic sentences or propositions and using certain logical connectives. So what those atomic propositions are and the logical connectives, they form the, those are the syntax, and they form the, they're used to define the language. Okay? So logic has a language. And in this case, these declarative sentences that are composed using these logic connectives and atomic propositions are called formulas. Okay? That's also another term that is used. And then there is another component which gives meaning, semantics, to the formulas or the sentences in that the language of the logic. This gives a way, defines some rules, a way of assigning truth values to well-formed sentences. And then the third thing that it has is inference rules, okay, of the kind that we are able to either derive conclusions like we did here, that in both these cases, not B, you could deduce not B, or checking tautologies like these, okay? So there are rules to derive conclusions and also conclude that something is a tautology. Okay? Now, if you study logic formally in a logic course, usually you end at these three things. Okay? In this course, we do study more than that. Specifically, what we use the SMT solvers, so which are automatic, decision procedures for deriving conclusions and checking tautology. Okay, so that's the fourth component, which will be the focus of this course. Okay, but in the next two, in the recap of the logic, I will introduce the first three things, so that you will get to know the basic concepts and the nuts and bolts of the first three components. Okay, today for propositional logic, the first two bullets here, the inference rules and the various automatic decision procedures, we will cover later. Okay, today I want to concentrate on introducing the first two components and also give you a flavor of how you could use propositional logic to model real life artifacts. And by introducing semantics, I'll also be covering introducing certain basic concepts that you would have seen and learned in a logic course, but to make sure that you you understand and okay. So first, propositional logic, the syntax or the language. Okay. Just like languages are usually defined. Okay, when the language has is a set of sentences, and when the set is infinite, you normally define it in a recursive or inductive fashion, starting with atomic propositions that belong to the language, and then how you construct using connectives, larger and larger formulas, that is sentences in the language. Okay. So there are two constants I'm introducing as part of this language, 1 and 0. They belong to this set of formulas. And for some finite set of atomic propositional variables belonging to the set vars, each element that is also a formula. Okay. Now, if psi is any propositional formula, then you can use the connective negation to construct not of psi, which also is belongs to the proposition, is a propositional formula. Then you can use binary connectives. Now, in the language that I'm defining, for every binary connective, which can either be the and, the conjunction, or disjunction, implication, or if and only if, two-way implication. So psi1 and psi2 are valid legal propositional formulas. Then the application of formula that you get by applying the binary connective is also a well-formed formula. So here's an example. So this is y and z implies not of x. Okay, so that's a well-formed propositional formula. Of course, this is not the only way to define language. There are alternative equivalent propositional logic language formulations. Okay, so here for example, it's not you can have just the 0, okay, and or an implication, because the negation will be, as you will see, will be defining the semantics of these connectives in such a way that negation can then be expressed in terms of implications as A implies 0. Another alternative equivalent language formulation is one in which you only have these two constants, 1 and 0, and implication. All the other connectives and or negation can be derived as can be derived in terms of these three things. Okay, and I mean, I already used certain semantic concept. I said equivalent language formulation. This equivalence is with respect to the semantics. And a side note that I want to make here is the semantics, the way I will introduce in the next few slides, they correspond to what is called, a version of propositional logic, which is called classical logic. So, we're not going to get into, there are other versions of logic, specifically something called constructive or intuitionistic logic, whose semantics is different, in subtle ways from classical propositional logic, which corresponds to what you're familiar with, namely two-valued Boolean logic or Boolean in algebra. The distinguishing aspect of classical logic is that it is based, A implies A. This is the law of excluded, it's called the law of excluded middle, is an axiom, whereas in constructive logic, this is not an axiom. So our semantics, both for propositional logic and the predicate logic, which we will see in the next class, correspond to the classical version of logic. So any questions so far? Okay. So now you have these syntax rules describe a way of constructing sentences in the language. Now, how do you assign meaning to these things? So what the semantics does is it defines truth value, which are denoted by true and false, for a well-formed formula. Fine. Given truth value assignments for the propositions or variables, propositional variables that appear inside in phi. So the notation we use is, given a truth assignment, then we say that phi holds, or phi is true, written this way. It actually means that phi holds or phi is true, so true, given x, z are true and y is false. Similarly, say that x, y, z does not hold in phi, which is also meant that phi is false, given x, y, z are true. That's what this thing means. So I want to draw your attention that I made a distinction here between these truth value, which are semantic concepts, true and false, and they are distinct from 1 and 0. 1 and 0 are so far only introduced syntactically. So, but they are formulas. They are specifically atomic formulas. So we need to define what the truth value of 1 and 0 are. So 1 and 0 and true and false are technically distinct. And that distinction is deliberate. And we will actually define what the truth value of 1 and 0 proper formulas are, what their meanings are. The semantics is. So variable assignments, as I've said, is just maps the variables inside that occur in the set vars to true and false, and they are denoted this way, variable assignment. So just like the syntax was, or the language, the sentences was constructed recursively, starting from atomic propositions, and then bigger and bigger formulas were built. The semantics, that is the truth value assignment for formulas, is also the rules for them are defined inductively or recursively, starting by specifying what the truth value for the atomic sentences are, and then defining rules that assign meaning to formulas that are constructed using the logical connectives belonging to the syntax of the language. It basically defines when a given assignment, for a given assignment S, phi holds, since phi is true, or for a given assignment, phi does not hold, because phi is false. So one, the atomic formula one is always true, okay, regardless of what the assignment is. So that's denoted this way, that one is always true and zero is always false. By always, I mean for for any variable assignment, this is that's the case. The other atomic proposition, sentence, the formula that you can construct in the syntax is the single atomic propositional variable. So that X holds in a particular assignment, given assignment, or it does not hold for any X belonging to the vars if S of X, that is the assignment that S, the variable assignment S makes for X, is true, and it is assumed to be false if it is the assignment is to that is false. So the rest of the rules define the meaning for formulas constructed using the various logical connectives in the syntax. So the truth value of not of psi, a formula, not of psi, is defined in terms of the meaning of psi. So not of psi, for a given assignment, truth assignment is true, holds, if for the same assignment, psi is false, okay, or it does not hold psi. Similarly, psi 1 and psi 2, the meaning of that, the semantics of that is holds, that it is true, if psi 1 as well as psi 2 are true in given for the assignment, as both of them have to be true. If either does not hold, then we consider psi 1 and psi 2 does not hold for the assignment, the variable assignment S. Disjunction, the OR is defined similarly, in a similar fashion. If either or both, if psi 1 or psi 2 hold for the variable assignment S, then, sorry, there is something, yes, okay, that's good, yeah. So then psi 1 or psi 2 holds in that for the variable assignment S. If not, that is, if both of them, psi 1 and psi 2 are false for the assignment S, then the disjunction is false. So now the implication and if then also else can be defined, okay, in this fashion. Okay, so implication is true for an assignment if this disjunction is true. So this way of assigning meaning to logical implication is part of classical logic. Okay? So any questions here? Okay. So this is, I've introduced it this way. So some of you might have taken discrete and have seen Boolean logic, Boolean two-valued Boolean logic, might not have seen this way of defining the semantics. So in general, in logic, the truth value of formulas are actually defined in this fashion. So I deliberately introduced it that way. But there is an easier way in this case for propositional logic to do, which some of you, I'm sure most of you are familiar with, and that is as a truth table. You can define the truth, give truth value assignments to the various propositional formula. Okay, and you can notice that in this case, one, the way I've defined this meaning of one, the constant one is kind of, since it is true for all possible variable assignments, it is equivalent to, in some sense, can be viewed as true and zero as false. So another way to, given that and the way the negation semantics is defined, that negation of one is zero and negation of zero is one, because of the way that this semantics is defined, negations and one and zero. You can also define the semantics in a different way. Let's suppose that given any variable assignment, okay, phi and a formula phi, say phi of square brackets s denotes the result of replacing every variable x in phi by 1 or 0. Okay, so here I'm kind of abusing the notation. So I'm substituting 1 to be true and false, and 0 to be false. And let's suppose that phi square bracket s is what you get by replacing every variable in phi by its truth value assignments. Okay, then you can simply define the meaning of, that is, the truth value assignments for phi for a given assignment by, I'm sorry, this should be phi square bracket of s. That's right. So yeah, that's correct. So by just saying, if phi of s is true, using the previous set of proofs, this is equivalent to just substituting 1 and 0 for the various variables as per the variable assignment, and then using the semantic rules of the logical connectives to simplifying them to either true or false. Okay, and that's also good. This is kind of a more that's what truth table semantics corresponds to. Okay.
Sir, I have a question. Like,
who's this?
I am Harsh.
Okay.
Yeah. So, what is the difference between these semantics and the previous symbols, like and or? Like, why have we defined this? Can't we just use and or and other things?
So they're exactly the same. The language is the same. I'm just giving you another way that you can assign semantics, which is equivalent to the previous way. So in the previous thing, that I expressed it by defining what this turnstile, a double turnstile, means by in terms of the truth value assignments of the subformulas. Okay, whereas here I'm saying another way to define is to take the formula and then you substitute 1 and 0, the constant 1 and 0. Okay, to it, and then you apply the previous rules on that substituted formula. Okay, that's all. Because earlier rules did indeed define the truth value semantics for a formula which had only ones and zeros, but were constructed using various logical connectives. Okay. Does that answer your question?
Yeah, it does answer my question.
Yeah. So all I'm saying is this is, you could use. I'm just saying it's this is what I'm describing here. Why it looks a bit convoluted here by saying what it means for each to be true by first applying it to the subformula. So here is when you describe what the truth assignments is using a truth table. What do? You just look at various, you plug in ones and zeros, right? For a particular value, in each row in a truth table corresponds to a particular assignment. Okay? And that's all I'm saying here. So you could use the previous rules as though you were evaluating by substituting 1 and 0 for the various variables, and then apply the previous rules as rules of simplification, okay, or evaluation. That's all I've stated. Yeah.
Okay.
Okay. So here are some concepts that if you're not familiar with it, you need to get acquainted. So we say phi is satisfiable if phi is satisfiable if there exists an assignment, a variable assignment S, such that phi of S is true. Okay, and this is written as S satisfies phi. That is phi, or phi holds in S. And we say that such a truth value assignment is a model of phi. So phi is said to be not satisfiable for a given variable assignment, and this is written as not of phi if, when you substitute that truth value assignment is false as per the rules of the semantics that we defined earlier. And phi is said to be unsatisfiable, written this way, if for every truth value assignment phi of S is false. And phi is valid, written double turnstile F without any variable assignment here, if it is for every possible variable assignments phi of S is gets assigned true as per the rules of the semantics. So with the way that we have defined the semantics, especially with the negation, phi is valid if and only if not of phi is unsatisfiable. Okay. Yeah, so these notions you should be familiar with, and since we will be using these things quite frequently. Okay. The way that we have defined the semantics of the various logical connectives, as I said, it corresponds to the classical interpretation of propositional logic, is, for that, all the usual laws of Boolean logic, such as De Morgan's law and various other equivalence, laws of Boolean logic, they all hold true. Okay, and so that's the way that this semantics has been defined. Yeah, so there are various normal forms. We'll get to this later on, but one particularly, the one that we will be using quite frequently, is the one where any Boolean formula, it's a formula expressed in this structurally in a certain fashion, is expressed just as in terms of a disjunction of a set of clauses where each clause, it's a conjunction of clauses. So we say a literal S is a variable X or its negation. And a clause is an ORing, a disjunction of literals. And a formula in conjunctive normal form consists of a conjunction of clauses. Okay. There are other, the reason that we call this a normal form is because any Boolean function over a set of variables can always be expressed using a formula in this that is fits this form, conjunctive normal form. There are other normal forms as well, which we will introduce as we go along. Okay, so here are some examples I'll start with, and so for each of these formulas, I want you to tell me if they are satisfiable, unsatisfiable, or valid. Okay, take this. So is it satisfiable? Anyone? Recall what satisfiability means. Means that there is a truth value assignment to the propositional variables in this that makes this thing true. It makes anyone?
It looks like it's unsatisfiable, but I'm not sure.
1, 2 being false and X being true. I think this works.
Yeah, say that again. So for example, if you make
X1 is false.
yeah, see, this is
X
in CNF. Okay, it's a conjunction of clauses. So in order for this to be true, since each of these clauses will have to be true, correct?
yeah.
So how do you make a disjunction to be true? At least one of those
X3
will have to be true. So you can make, for example, X3 to be false can make these two to be, the last two clauses to be true. And you can pick X2 to be false, okay, and make the second clause to be true. And then you can pick X1 to be true. So,
sir, if X2 is false, then in the last clause, X2, X3 both are false. So that won't satisfy.
no, if X2 is false, no. If X2 is false, not of X2 will be true, correct? Therefore, this one will be, this clause will be true.
The first the second one, X1, negative of X1 and negative of X2. From the one written right, I think that will not hold because both are false.
See, X1 being false means this will, X1 being false means this will be true. And X2 being false means both these things will be true. Correct? I mean, X1 being false makes this and the second and the third clauses to be true. X2 being false makes the last one to be true. Then I can pick X3 to be true, correct? I'm making X1 to be false and X2 to be false, okay?
Yes, sir. I'm saying in the second bracket, X1 or X2, so both here are false.
Correct.
So will that hold? That will be false, no?
Why? Because
there is not of X1. So not of X1 is like true now, right? Because X1 is false.
X1 is
so
false, therefore not of
X1
X1 is true. So a disjunction is true if any one of them is true. Therefore, this is true by virtue of the fact that X1 is false.
Yes, I got it.
Yeah. How about this one? This happens to be valid because, see, X1 is either X1 is true or false. Okay, if X1 is false, then this implication, the first one, this one is true. So the meaning of the semantics of implication is defined in such a way that if the antecedent X is false, the whole thing is true.
Is this valid, right? I think.
Correct. This is valid. So if X1 is false, the first disjunct is the first argument to the OR is true. Therefore, it becomes true. And if X is true, then The second one, which is a disjunction with X, it'll be true, and therefore this is valid. Okay. So then it doesn't matter what the assignments for Y and Z are. And that's why this is true for all possible truth value assignments. Now, this is an example where it is not, this is unsatisfiable. Why? Can anyone explain? Once again, this formula is in CNF. It's a conjunction of
Sir,
yeah.
Sir, if we take like C bar, C not to be true.
Yeah, C bar has to be true.
Yes, C bar has to be true. Then
yeah.
we'll get C is false. So for the first bracket to hold, B should be true.
Correct.
And since B is true, B not will be false. So in the second bracket, A has to be true.
Correct.
And in the third bracket, we get A naught is false and C was already false. So this will not hold.
Good.
Which is unsatisfied.
Yeah, so that's why it is unsatisfied. Okay, now we move. I want to move now to, so this is given a formula, whether it is satisfied, unsatisfied, or valid, that's easy to check. Okay, all you need to do, like I already gave you, a quick way to do, you just plug in, okay, once and the truth value assignment, and then you apply the semantic rules, okay, to check if it is satisfiable. To check validity, you have to check for all possible assignments. Now I want to move to using logic, this as a modeling device to construct formulas that model scenarios of the kind that we saw in the first slide. And suppose we have three variables, because that's important for this for this course, and that's what we'll be doing in verification. Okay, specifically, we will be modeling neural networks, for which you need to get familiar with how you can use logic to model. By modeling, I mean a given problem you should need to construct a formula that somehow models the scenario, and such that the problem that you want to solve can be expressed as an instance of checking that a particular formula is either satisfiable, unsatisfiable, or valid. Okay, so that's the kind of examples that I will introduce now. Suppose we have three variables, propositional variables A1, A2, and A3. What I'm asking you to do is to construct a formula that is satisfiable if and only if the following condition holds, okay, each of them separately. I want you to construct a formula which is satisfiable if and only if at least one of these propositional variables holds, that is, if it is true. Chat. Yes, okay. A1 or A2 or A3, that's correct, okay. So you see, if A1, A2, so there are various ways this particular formula good. Okay, so A1 or A2 or A3. So the various possible assignments that make this thing satisfiable, each, and the only one that makes this, the only assignment that makes this unsatisfiable is when all of them are zero. So this is models the situation, the scenario where you want at least one of the propositional variables to be true. Exactly one is true.
we can have different conjunctions, as in like if A1 not of A1 and A2 A3, then again or of uh, A1 and like not of A2 and A3, and again A1 and A2 and not of
Yeah,
A3.
that's one way to. That's what. Yes. Okay. So you have to take. You have to make sure that only exactly one. That is one way to do. You got the idea. So here is kind of an equivalent, but another. Since you already have at least one, so at least one has to be true for this. For exactly one to be true. Additionally, you cannot have the situation pairwise. You cannot have a situation that two of them are true simultaneously. Okay, and that's what this prevents. Okay, it says that pairwise you can't have two variables to be true. I mean, yes. So what you said, I don't know who said that. That is equivalent to this, where you were using all three variables to construct them and enumerate them. Yeah. How about at most one?
A XOR B XOR A1 XOR A2 XOR A3, and then you can write XOR in terms of logic.
You mean exclusive OR?
Yes, yes.
Exclusive OR. I mean, at most
We just
one,
need to make sure that like
at most
no
one. Notice at most one also includes it's all of them being zero. Okay, so that's the.
Okay, XOR might not work. I think I made a
Yeah.
mistake.
So at most one is exactly one. If weakening, it's like
we can
either
just
some of them is
take
zero or exactly one. Okay, so that's
Yeah.
what at most one is true. So I think what you were saying exactly one can be captured using nested exclusive OR. Okay, this one I was aiming for at most true, which is exactly one plus one more situation where it should include, which is the case when all of them are zero. Okay, so this is, yeah, so as a first exercise. Okay, so this is the kind of what I wanted even before I get to the other two components of propositional logic, which is deduction, how do you inference rules, and how do you actually procedures to check these things. I want you to get familiar with the how you use these things to model realistic artifacts and scenarios, so you could then solve certain problems using SMT solvers, which will be your first exercise. Okay. So I will now, in the remaining thing, introduce a couple of more examples. Okay. So what we want to do is to model using propositional logic the 8 queens problem, or solution to. What I mean by that is to solve this problem, is it possible to safely place n queens on an n by n chessboard for some specific finite n? More specifically, what it means to model this problem, a solution to this problem using propositional logic, means construct a propositional formula whose satisfying model is a possible solution to this 8 queens problem. So that's what you're being asked to do. So whenever you're faced with this kind of a situation, the first thing is you have to choose these propositional variables, okay, to model these, the basic, the atomic propositions that are relevant to express your problem, okay, your scenario. So in this case, what you need is your variables you have to model the situation of a queen being placed in one of these, assuming that we have an 8x8 board. There are 64 possible positions depending upon the location, the row and the column location of that position on the board. For each of them, we associate a variable. And the meaning of that variable, the semantics of that variable, if it is 1, it means that if and only if there is a queen placed at that position, at row I and column J. So we're using, for an 8x8 board, 64 such variables, each of which can take 1 or 0. And if it's 1, then it means that there is a queen. Then the next thing is, then you have to model all the required constraints that the problem has to satisfy. And you need to include that, each of those constraints, as the subformula. Then, and the conjunction of all those constraints will make your an overall formula that models the whose satisfiability will then be in this case will be a solution to the thing. So I'll give modeling one such constraint now, and I will leave as an exercise for you to model all the other constraints to model this problem completely. So if Xij is true, that if there is a queen, these two constraints model the row and the column constraints of the 8 queens problem. So if you have placed a queen at location ij, row I, column j, then you cannot have, this expresses, then you cannot have any queen for it to be safe in the same column, okay? And that's what this thing expresses. So if X of ij is true, then for all L, that is, okay, for all the other positions in the same column, okay, that is, for all j from 1 to n, that is different than I, that should be, there should not be any queen, which means that has to be false. Okay, that's what this constraint specifies, asserts. Similarly, I mean, there should not be any queens in any of the other locations in the row, okay, in R, and that's what this expresses. So similarly, in order to complete this problem, you will have to specify the other constraints for diagonal constraints. Okay. So remember that. So here, this is, I mean, I've expressed these constraints as like a schema, okay, where it is being iterated over the variables I and j. But in order, since our formula has to be finite, okay, so for any given specific situation of like 8x8, I mean, since I'm allowing the size of the board to be a parameter, I'm expressing it as a schema where it generates this formula for any particular n. So you could instantiate this schema for a particular value of n. Then it will be a finite number of formulas. So for example, if I instantiate this for I is equal to 8 and j is equal to 8, 1 to 8, then I'll have a finite formula. So as an exercise, I want you to now, I mean, define also the constraints that assert the the conditions that have to be true to ensure that there are no queens in any of the diagonals where you have already a queen. Then you take the conjunction of all these, each of these constraints, and that will be your mega formula, that whose satisfiability, whose satisfying instance will give you a solution. Now, since the 8 queens problem is indeed solvable and has multiple solutions, this indeed, that formula that you construct will be satisfiable, and there'll be multiple satisfying instances, each of which will be a possible solution. And you can actually check that. Okay, the first exercise that I'll be assigning, that we'll be assigning you, will be to complete this by giving all the other constraints, and then use it with an SMT solver. Any questions here? So you got the idea of what it means to model. This is what I mean when you have to define the variables to denote various things. The propositions, the declarative propositions that are relevant for the problem, and then you have to construct a formula that characterizes, whose solution characterizes the, whose satisfying instance characterizes as a solution to the problem. Some cases here, we are the satisfying instances happen to be the solutions that you're looking for. In some problems, as we will see, maybe in the DNN verification problem that you saw, Diganta described, the verification was expressed as a validity problem, okay? That some assertion had to be valid for all inputs. Some constraints at the output of the DNN had to be true for all possible input values, and usually that is expressed as the validity problem of a suitably constructed formula. Here, it happens to be the satisfying instance. Any questions? Okay, another problem which you will be, which I'll be assigning you working on is modeling Sudoku. Okay. So once again, here the goal is to construct a propositional formula whose model is a solution to a given Sudoku problem. So what should the variables be here? Anyone?
We could have xij's. Like, are we allowed to work with integers?
Suppose you describe in terms of numbers, digits, okay? Since there are only finitely many digits, well, that's one, kind of an issue, technical issue you have. But since there are only finitely many, okay, let's assume that you'll start with digits, okay? As long as you have a discrete number of finite number of discrete elements, you can always encode them.
You could do that with xijk, where k is from 1 to 9, right? Yeah. And if it is 1, then there is an integer.
Yeah, so you will have variables, correct? Okay, so this is exactly what you said. So ijk will be each of them will be ranging from 0 to 9, okay, from 1 to 9. And Vijk will be 1 and k is also from 1 to 9. That's the digit that is placed in that cell. So, but of course, this itself has to be a propositional variable. Okay, so we'll have to say that Vijk is equal to 1 if column I, row J contains the number K. So I made this thing in as indices. Maybe you had a different idea, okay? So, is this the one that you had? Whoever that.
Yeah, this was the one I had.
So for each of the possible digits that can be placed inside that cell, I've introduced a separate propositional variable. So in this case, there are 9 times 9 times 9 number of variables. This kind of gives you an idea. You see that this encoding, there is a lot of thought that you need to put into, because as the number of variables, because the SAT problem, as I mentioned, still, although there have been a lot of breakthroughs, and you can, present day SAT solvers are able to solve formulas that have millions of variables. These things, in a real situation, the number of variables needed can grow very fast. So, good way of encoding using a clever way of defining these variables gets you, can save you a lot of things. There are a lot of, if you're clever about it, there are compact ways to encode these problems. So I'll only show you one constraint here, and then as exercise, I want you to work on the other constraints and then try this out also as part of your first assignment. Value in each cell is valid, which means it has to be one of those 9 allowed digits. Okay, that means since I've defined Bijk to be 1, if exactly one of them has to be 1, because you can't have 2 different numbers sitting in the same cell. Okay, so that is one kind of a sanity constraint that you should have. You can't have 2 digits, 2 distinct digits inside the same cell. That's what this thing, this constraint expresses. And you already know how to express this, correct? I've expressed it as a sum.
This is exactly 1.
Exactly 1. You're exactly right. Okay. So although I've expressed it as a sum, it is exactly 1 is the formula. Now similarly, now you have to express other constraints, that every row and every column in this grid has a unique digit. There are no repeating digits. That is something that you have to express. And then the similar constraint on a 3 by 3 grid. So those two are the other set of constraints. Then if you take a conjunction of all those constraints, because you want all of them to be simultaneously true, then any such thing will be a satisfying solution. Now you can also then make it interesting. You could give certain numbers. You can make an actual Sudoku problem by actually adding additional cell constraints where to specify that certain cells have certain numbers, and then generate your modeling. Your problem will generate a solution. Okay, solution for that. Yeah? So this is something. So I think I want to end here at 4:45. So if you have any further questions, I think I don't want to click anymore because if I did, I'll be giving out the solution. Okay. So yes. So next time I will do the same thing. Okay. I will introduce the syntax and semantics of predicate logic, specifically the multi-sorted predicate logic that we that is the logic that SMT solves, multi-sorted predicate logic for certain specific kinds of sorts that are the target of solving for SMT solvers that I will introduce. And yeah, after that, I will, both as a syntax and semantics of predicate logic. And then, yes, for some more problems that you can do using SMT solvers. Here, this is all Boolean problems, and here we're expressing it as Boolean satisfiability. So there it will be the satisfiability in multi-sorted predicate logic. Then we'll be getting to the deduction part, okay, and how that the checking of satisfiability or unsatisfiability in validity can be done using specific procedures, automatic procedures. That will be the theory part of this course. The modeling part will be then about DNN and what it means to verify and so on. So that's the other component. So anyway, next class is a recap of predicate logic. Any questions?
Sir, I have a question. So like you had given a book on like logic, added a book on logic to the Moodle site. So how many chapters should we be familiar with in that?
See, that's only a supplementary book. Okay, the book on logic. Actually, I haven't even read that. Okay, I started reading it, and actually, the first the motivation, the example for motivation, I picked from there and just changed the name. The thing, no, but that's a good book. Okay, so I think certainly the first two. Okay, the first two chapters is what you will need there. After that, it goes on to talk. I'll have to look at that, and then I will say certainly the semantics, the propositional logic part, and the semantic syntax. There could be some small differences in the way that the notational differences in the way that I've used. But I think you don't need to know get into the detail of completeness and so on.
Can we leave that part out where it tries to build a SAT solver?
No. Okay. The SAT solver part, that chapter I have to check, okay, as to what it does. For the SAT solver part, we will be getting a little bit more detail into it. For that, I'll actually be using the chapters from the decision procedures book. Okay.
Okay.
I mean, I'll be following that very closely. So for that part, as to what SAT solvers do, I have to check exactly what that thing does. I mean, and I gave that as, for the basic concepts of logic, like satisfiability, validity, and so on. And to some extent, what it means for a particular system of inference rules, which we'll introduce. Okay, that part, would be useful. If you want to get a little more deeper into that part, that is where that book is intended for. Okay. Now, the SAT solver part, I don't think, will be using the decision procedures.
Okay.
Because, yes. Okay, so here in this book, I don't know what the chapter on SAT solvers does. I will go through that. I don't think I suspect that chapter does not have as much detail as the decision procedures book. But what it will have, which you may want to do as a supplementary reading, is what does it mean to derive proofs? Okay, to make proofs. Okay, now they go into natural deduction, some inference rules. We will very quickly cover that. Okay, now for example, that book, and I don't know if it has, maybe the SAT solver does have. There are different kinds of inference, a system of inference rules to construct proofs that check validity and unsatisfiability. Okay, one such is natural deduction. There is another inference rule called resolution. Resolution is the one that SAT solvers are based on. Okay, that we will be covering more. Okay, natural deduction is something that is good for doing proofs by hand, but not for building automatic decision procedures. So we will be focusing more on resolution. Now, if the chapter on SAT solvers in the logic supplementary textbook indeed talks about resolution principle there, then that will be relevant. Okay, that I'll be covering in class also. Okay, not right away, but as and when we introduce SAT solvers. Okay, in that section. But I will be following the decision procedure chapters from the decision procedure book very closely, for that.
Okay.
Okay. Any other questions? Yeah. Okay. Since I assume that, okay, let's see how many people show up in the class. There are what? So let's see, I'm going to stop sharing here. So how many people are here? 1, 2, 3, 4, 5, is it? How many people? Actually, only 5, isn't it? 1, 2, 3, 4, 5. Yeah. What's the? There are only 4 people. So let's see, if it's only 4 people that show up, then maybe we are more flexible. So let's wait until next class. How many of you, the 4 here, are serious about the course?
I am. Deep.
Yes, even I'm going to.
Yeah.
I am also.
Give your name before you say. Yeah, there is.
Deepchi.
Abhishek Mishra, sir, I am.
Sure.
Yeah, Harsh, how about you?
Yes, sir, I am serious about this course.
Okay, so 4 of you are serious, correct? All the 4 that are saying. I think there were a couple of more, weren't there? I thought Arpan was here. He's not here. I mean, he did join. So let's wait until.
So there is another course which I'm taking, which is clashing with this. That is like FML, like Foundations of Machine Learning.
Yeah, that I thought.
So,
okay, so if it's
yeah, so
if any of them are, yeah, I'll send an email. If that is causing some people to think, then since this is a smaller class, I could, we could move. Who's here for the 4 of you? Who's it clashing with?
for me, Deepchi.
Yeah, sir, so I'm not crediting Foundations of Machine Learning, but I still do want to attend it. So it would be
I see. So that is still the thing. So we will have to move. Okay. Yeah.
Sir, in my case also, I'm from MSc Data Science first year. I don't think the faculty will allow me to have a credit of this course, but still, sir, I want to do the course.
That is actually not true. Have you checked with them?
No, they were saying that we strongly recommend that people of first year, especially first semester student, does not take an extra course in the first semester. So I don't think they'll allow, but if they allow, I'll attend. If they don't allow,
Yeah,
I still want to attend the class.
Okay, that's fine. Yeah, okay. Okay, so let's wait for a couple of more classes so that we will know. Okay, it's a small class, so then we can do more intimate planning. Yeah. Okay.
Yeah, I think a lot of people who are not here might also have, might have not been able to attend because of the other TFML course.
Yeah, but the reason I doubt that is because, I mean, you might be right, but they would have at least filled out the questionnaire, no?
Yeah, that's true. So let me check how many things are
Yeah, you could check informally, and you could even send an email to see. Oh, I mean, I will send an email to see how many people that are interested in taking the course didn't attend today due to clash with the other one. I suspected some might have been okay. Well, let's yeah. So based on that response, and then the thing we'll see. Yeah.
Yeah, okay. I think there are a few more responses in the question. I think it's up to 7 now.
Ah, I see. Okay. But regardless, I will send the thing and then see what number it settles down to. It'll be nice if we have a few more. So then we can actually, if we have only up to 6 or something, we then don't need to pair up. Okay. We have more flexibility, right? Yeah.
Yeah, I think
Depending upon what the thing is. I mean, you could still assign different things. Let's see. So that is still some ways away. Yeah. Okay, I'll stop sharing. I've already stopped sharing.